Hello, hi, welcome back. Before I introduce Paul, I just want to say the last session we had a technical issue, which I apologize for. We have recorded the presentation because it worked fine on StreamYard. For some reason, it didn't connect, and we'll have that up as soon as we can. Oscar Wyatt did a great job, and he will respond to any questions you may have, and we'll make sure that we facilitate that. Anyway, moving now on swiftly to our penultimate session. I want to introduce Professor Paul Groth. He's from the University of Amsterdam, and he's going to explore some really interesting new work that he's doing. Paul has done research in universities around the world and at Elsevier Labs. And Paul's subject today is he's going to talk about content and signals, the value of the entire data estate for machine learning. Over to Paul.
Hi, everybody. Thanks for having me, and thanks for coming along. So what are we going to do today? So I want to give you a bit of a background about where I'm coming from. So a little bit so you get a feel for my thinking here. And then I want to talk really about the success of machine learning. I'm sure you've seen lots of great examples throughout the week of the applications of AI, but I just want to revisit that. And based on that, I want to talk about the need for data and, in some sense, how we think about data in the context of acquiring that data to build AI models. And given that idea, I want to talk to you about what is that in terms of implications, especially if you're a content-oriented business, and some quick actions you could take to essentially make yourself AI ready, and to think about your business or your organization as an organization that's primed to take advantage of machine learning. So first, a little bit about my context. I'm a professor at University of Amsterdam. I run a research lab, but more importantly, for this talk is I'm partnering with industry often. So I'm a scientific director of two what we call ICAI labs. So these are labs within the Netherlands focused on doing AI with industry. And in particular, I'm co-scientific director of the Discovery Lab, which is an AI lab with Elsevier. And I'm also co-scientific director of the AI for Retail Lab, which is a research lab with Ahold Delhaize, which is a large grocer internationally. And what these labs do is they essentially have 5 PhD students working on core AI problems for companies. And I think that gives me an interesting insight or interesting perspective on how research can really connect with these problems in industry. And interesting, this kind of format of PhD students working directly on industrial problems or organizational problems has really flourished within Amsterdam. We have 5 locations, and I think right now 12 or 15 of these AI labs. So that's a bit of my background to give you context for the talk. So first, machine learning. And I think it's really important just to go back to the fundamentals of what machine learning is and how it changes the game in terms of how we think about the design of software and technologies. So machine learning is fundamentally programming. And our classical way of thinking about programming is we have some input data sets, we have a programmer, right? A software developer who writes an algorithm. That algorithm is combined with input to produce some interesting output, right? And we have software development routines, programming routines to do that. With machine learning, it's a different way of programming, right? So we see this on the bottom of this slide where we have a learning architecture, right? So that's a kind of a space of the kind of models we developed. We have some data. We give that data to that learning architecture, and we try to learn the program. We learn the algorithm. We learn the function that produces some model. And now that model is now our algorithm, right? And then we can give input to that model to produce some new output. So here we've, in some sense, replaced the programmer with this process of training a model, right? Having a learning architecture, having a data, and training that model. So here, in some sense, yes, we still require programmers for a lot of different things, but here the fundamental currency is not programs, but data. So data becomes the central notion, and that's going to be the theme of this talk. How do we get data? How do we get the right kind of data? And how do we use that data to help us do new pieces of software? So that's machine learning. You're probably aware of that. So what machine learning has done in the past, over the past decade, in particular the past couple of years, is really accelerated what we were able to do in terms of artificial intelligence. So I like to give the examples of machines being able to read. So this is an example from Allen NLP, and you can actually go and do this demo. This is a passage from that describes the Matrix movie, right? So you have just this text. The Matrix is a 1999 science fiction action film, so on and so forth. And you can ask questions, just natural language questions about those passages. For example, who stars in the Matrix? So we can just do this, and it will actually answer your question, right? So it will say Keanu Reeves, Lauren Fishburne, and so on. And that just is extracted directly from that passage, right? So literally the machine, based on machine learning, is able to read that passage context and answer your question of who starred in the Matrix. And this happens all over in terms of this kind of ability to read, to see, these kind of human-like capabilities are being progressively extended and are at performance levels that are just really, I have to say, amazing. So this is an example of performance. So this is the so-called glue benchmark. And I don't want to explain the whole thing to you, but the glue benchmark is a series of natural language processing tasks. So this notion of reading that are put together. And this is a leaderboard, what you're seeing here, a leaderboard of who's scoring the best on 10 different, I think, natural language processing tasks. Now, the important point is the red I've shown you. That's human baseline scoring on these different natural language processing tasks. So the tasks you've seen before, question answering, seeing if sentences are similar, these are the kinds of tasks. And you see that the score here is 87 for a human, and our models, right, our machine learning models are actually performing better than these human baselines, right? So this just tells you, how far we've come in this capability to do these kinds of human level, human style tasks, whether it's in natural language processing, which you see here, or in computer vision. And maybe you've seen this in your own work, this ability for machine learning to really accomplish things on different tasks. This capability, the capability for machines to see and machines to read, has really been driven by deep neural networks. So these kind of ability to essentially not have to do feature engineering, but the ability to take data, right, learn from representations from that data and apply and learn models, learn these fairly complicated functions, these complicated algorithms in order to do these kinds of downstream tasks. And this has really been a revolution. And the revolution in deep neural networks is not only about the ability to have large-scale compute through things like GPUs and the ability to think about new language architectures for these networks and ways of programming these networks, but I would claim that a lot of this is through the availability of data. And we see this with these NLP models. So the kinds of models that I showed you before that were scoring above human level performance, these are massive models, right? So if you think about BERT, which is a large scale, what's called a transformer-based model, that's doing these kinds of natural language processing tasks, these are massive, massive models, right? So you're thinking something about 17 billion or 8 billion parameters to these models. They're looking at between 2.5 to 35 billion words, right? Training volumes of tokens in the trillions of range in the actual text you're looking at. So just massive, massive models using massive amounts of data. And essentially by using this massive amounts of data, we can build these human level performance models. Now you might be looking at the slide, and I think a thing to see in the slide is the cost of building these models, right? So to train 110 million, to train these state-of-the-art models, at least cost you between $2,000 and $50,000, right? To train the most state-of-the-art models today, you're thinking upwards of 80K, and maybe for things like GPT-3, millions of dollars to actually train these models, right? So to get this human performance, we need lots of data and we need lots of compute power. This need for data, we see this over and over again, and it just keeps these deep learning models are just completely data hungry. So this is an example from images, right? So what we can see is the data sets, many hundreds of thousands or tens of thousands of categories, but per category, right, we need tons of instances. So a lot of example data sets to actually get the performance. So if you look at the Coco image data set, you're thinking above 10,000 or way above 10,000 instances over hundreds of categories. And we not only need lots of data, typically we need lots of annotated data. So classically for a task like relation extraction, we need something like 100 of thousands of hand annotated examples. And typically we use crowdsourcing for it. So we need somebody to go in and say, in a sentence, this person is founded in an organization, and we need to annotate that. And that's really been one of the more expensive parts of this whole deep learning revolution. Where do we get lots of data, and where do we get lots of annotated data? And the problem is annotation itself is expensive, right? So currently we're running a competition. So like the leaderboard competition we saw, we're running one of these competitions about extracting units and measures from scientific text. And the interesting thing here is we're actually doing this annotation. And my colleague, Corey Harper from Elsevier, has been doing these annotation campaigns, and it's really tons and tons of work. He's been spending almost this entire year working on this annotation. And you can see, oh, I need one of these examples. Oh, measured entity, I need to annotate the quantity, a measured entity, another quantity. That looks pretty easy. But if you go to these complicated situations, you get things like this, right? Tons of quantities, tons of measured entities, and people have to go by hand to go annotate this data. And you annotate, as we saw, a lot of them. So this is really the challenge. How do we reduce fundamentally the cost of acquiring lots of data, right? And acquiring lots of annotated data. So to reduce the cost of data, I think if you look at web scale companies like Google or Amazon or Apple, they look at the web, right? So they gather data to the web. For most companies that I talk to, I think the cost of data is use what you have. So I think a lot of companies already have a lot of data that they could use to train these models or to fine tune these models. But the real problem is the cost of annotated data. So how can we get more of this labeled training data? So what I want to walk through with you for the next bit of the talk is how we can get more label trained data. And I want to look at 3 ways of doing that. One way is what we call transfer learning. So this is using models already trained on a different task to do a new task. The second way I want to talk to you about is active learning. So instead of building all the training data up beforehand, we ask the model, hey, what do you need to actually get better? What kinds of data do you need so that we can train you on the fly actively, right? So this reduces, again, the need for label training data. And lastly, I think this is kind of the core of the talk, is to talk about weak supervision. So ways of getting labels from other parts of your data estate in order to get this annotated data. So transfer learning, active learning, and weak supervision. So transfer learning. So what is transfer learning? So instead of training for years on end, weeks on end, our own transformer style model with all this data, we leave that up to others, right? So luckily, people like Google or people like Facebook or people like Allen AI, they actually train these large-scale transformer-based models, and then they put them on the web, right? And then you can do things. So this is an example we did looking for detecting adverse reactions in scientific text. So you can see the sentence over here, and it says other GLP-1 receptor antagonist XYZ and treatment duration dependent thyroid cell tumors with adenosis and carcinomas in rodents, right? And so what we want to be able to do is detect whether that's an adverse reaction, right? But we want to do this at a large scale. Unfortunately, to actually gather this kind of training data is expensive, right? You need somebody who can read this sentence and actually underline or label those things, right? But by using transfer learning, we can use a lot smaller examples. So for example, here we're looking at thousands of sentences. So 4,000 sentences in one corpus or 3,000 sentences in another corpus. And by using an existing model, these existing transformer models, we can essentially fine tune that model to the task of, in this case, detecting adverse events. And we get really good results, right? So plus 10%, plus 13%, plus 6%, but without a lot of data, right? It's much less training data. And this notion of transfer learning is really accessible, right? So there is a company called Hugging Face, right? And this is something you can check out if you're a software developer. They make these large-scale models like GPT-2 or BERT. They make them available in pretty simple Python packages. And so you may have heard of these, the ability to automatically complete sentences, so automatically complete text. So this here is an example where they retrained or they fine-tuned one of these models on archive papers, right? And you're able to actually go there and try this out, type a sentence, and it will try to auto-complete the sentence for you in full sentences. And these models are available pretty much in a not very much Python code. So this is a way we can drive down the cost of training data by relying on other people's large-scale models. So that's transfer learning. The second way I talked about is active learning. So this is an example of this units and measures idea. So active learning, what happens is as you go as part of the annotation process, so you have annotators, they annotate, and essentially the model essentially tries to already predict various features of the text. In this case, saying what a quantity is or not, right? And you can say, okay, you're correct or not correct. And an annotator can go quickly and say correct, not correct, correct, not correct, and give feedback to the model. So this is a really fast way of training a model quite quickly because you're not having to the model is telling you exactly the kind of data it needs, and you're giving feedback directly to the model. So this is a tool called Prodigy that helps you do this. There's a couple of other different kinds of tools out there that help you do this active learning style gathering of data, right? And I suggest that this is really one way to really rapidly build models. And I think if you're doing testing in machine learning space, I think especially around natural language processing or image recognition, this is really a powerful way to do ML in your space. The last way I want to talk about, and I think this is really important when you're thinking about your data state, is this notion of weak supervision, right? So what is weak supervision? So weak supervision is what we're going to do is we're going to look at related resources that we might have to use as essentially signals to help us label data, right? So you might have an existing taxonomy or semantic categorization. You might have a knowledge graph. You might have some statistics, right, from users users using your website. You might be able to write down little tiny rules or heuristics about your data. And I'll show you an example in a bit. And using all these kind of different resources, what we can do is use a tool to kind of look across those resources, look for commonalities about our labels, and then are able to essentially generate training data from that. So we weekly generate these kinds of training data. It may not be as precise as our hand label data, but by using different sources, we're essentially able to kind of combine those multiple sources to essentially get the performance we need. So this is an example from Google where they did product classification and topic classification. And the orange bar here, or the fully supervised, right? So this is where we actually have training data, starts out lower, right? And the orange is this weekly supervised. So with much less data, so in the case of topic classification, 25,000 examples, right? You're able to get, with this kind of weekly supervised approach, much better scores relatively to a completely fully supervised approach. Now, what are these weak, and what's nice about weak supervision is that you can do this at very small scales, right? Again, so this is an example we did with actually humanities colleagues, where we're trying to extract smells from 19th century textbooks, right? So things like the scent of tobacco. And here, again, we use this kind of weak supervision approach in order to build up the signal to help us do this kind of information extraction. So what do these supervisions look like? Well, oftentimes they look at like little tiny programs that you might write. So for example, here's a little a program that you would write that's able to find a disease, right? So for example, if you find chemical A and disease B in a sentence, just return true. Now you might say, well, is that always going to be the case, right? If we're looking for the cause of a disease? Well, maybe sometimes true, or maybe not, but it gives us some indication that that might be the case. Or just write a little expression, find cause in your data set, right? A little regular expression. And if you find that cause, then actually return a label true. So you write these little tiny functions, very simple things that you can ask experts to do, right? Not too hard. And they generate these forms of supervision that we can use to kind of label our data sets pretty simply. So we can use multiple different sources or signals. We can use heuristics and rules. So human authored rules, experts rules. We can use existing machine learning models that we have for a particular domain. So we can use topic models or taggers you might have, or classifiers to actually generate these kinds of labels. As I said, you can use aggregate statistics, right? So we can use these statistics to tell us to label things, or we can use knowledge graphs or databases that have something about our domain. And we can combine all those to help us label our data sets and then learn these machine learning models. What's neat about this is that going forward, we can see that we're able to use multimodal data. So this is an example of combining radiology, images, EEG signals, but also notes from practitioners in the case study of radiology, where combining these annotations from different data sets, we're able then to do better at classification or in different domains. And what we're seeing is that the barrier to doing this sort of labeling, this sort of weak supervision, is going down rapidly. So this is an example from one of our collaborators where they were looking at doing end user data programming. So just having users actually annotate things and build these kinds of functions in a user interface, right? Not programming directly or having to train the model, but this rapidly then decreases the cost of even acquiring these kinds of weak supervision signals. And most radically, what you're seeing is the ability to just use, observe people and use that as supervision signals. So here's an example where they're using eye gaze, right, to actually help improve the recognition of, help improve image recognition, right? So the eye gaze here is the heat map, and if you're focused a little bit more, it helps the model learn by this eye tracking to understand what grilled salmon is or French toast is. So essentially the cost of capturing these signals is going lower and lower and lower that we can use to then do this supervision. So what's the implications of all this? What's the implications of lowering the cost of acquiring this kind of using these signals to do the training of machine learning? So the first is that we have an improving ability to use expertise, right? And doctor looking at a looking at a radiology image, an expert writing or using an interface to create these rules. So the consequence is that expertise is a critical resource. With our ability to use more and different signals, signal capture becomes imperative. So in your organization, you need to think, hey, how can I do this kind of signal capture? So we are being able to use multiple content sources to do better machine learning, but that means you need to be able to understand and use all the data within your data estate. So the more content you have available and the different kinds of content, that becomes more valuable. And finally, because machine learning at the state of the art is much more accessible, the problem becomes not about machine learning per se, it becomes about formulating the problem correctly for machine learning. And this is kind of a fundamental, I would say, trend, right? So with a couple of co-authors, we've been promoting this idea of a knowledge scientist, and this is really about saying that the data is becoming fundamentally the important pig. How do we use the data we have? How do we organize the data we have such that we can use it in these machine learning pipelines, right? So it's not about applying machine learning. It's more about understanding the data we have and the signals that we have coming from our interactions with our customers. So I'll leave you with two actions. So first is make a map. What are the kinds of sources of data you have? What are the kinds of data you have in your data estate? Where are your experts? Do you have curators? Do you have professionals? How can you understand where you're getting all the signal from? So make a map, number one. I bet you have way more signal and way more data that can be used for ML than you might think. Action number 2, this is a great problem. It's not really now about, hey, we're going to have AI to replace people, but more, how do I combine the customer-centric, the product-centric, the domain-centric expertise I have with these kinds of machine learning applications. And things like weak supervision and transfer learning help us essentially translate that expertise into performance, right? So it's really about understanding your domain problems, understanding where your expertise lies, and then using these new tools to translate that into models. So in conclusion, powerful machine learning models are available today. The data is the essential driver for applying AI. And I would encourage you not to overlook your resources. Your content, your expertise, your customer insight are really critical. I think every company can be an AI-driven company, a machine learning-driven company, but it's more about understanding the resources you already have in the context. And things like weak supervision are really a way to help you apply machine learning in your content-based company. And with that, I think I'm done.
Pretty much on time, just slightly over, Paul. Thank you very much. Very instructive presentation about some really interesting new work and interesting issues. Making machine learning better seems to be a really important area. We have got one. I just want to throw one really practical, quick question at you from Ian Mulvaney. You talked about annotating a lot. What annotating tool are you using? When he was at Stage, he invested in TagWorks and evaluated a ton of others. And he also says Snorkel is good. So do you have a response for Ian and the audience?
Yeah, I mean, a lot of the work I was mentioning here is essentially Snorkel, right? Snorkel is a weak supervision programming environment, I guess I would say, or a package, and it's very useful. And they also have a new company. I haven't used those tools. For annotation, we also often use, we've liked Prodigy is nice as a tool. And also then just for old school annotation, we use Brat if you want tools.
Excellent. I'm going to have to draw the line there because we are running out of time. Just as a general thank you to Paul, brilliant presentation. That presentation I'm sure will be up fairly soon. Oscar's presentation that didn't work on the StreamYard is now available to view in the library. So please do go there and file your questions when you get time. I'm going to wrap up this section. The final session will start straight away. And that's going to be Tommy Doyle, who's a Content ambassador, introducing Esther Dyson, angel investor, renowned author, publisher, TED talker, and healthcare expert, just to finish off where they think content and AI are going to go. Thanks, Paul. I'll talk to all of the audience at the very end of the day. Speak to you soon. Cheers. Bye-bye.
Thanks, everybody.